In a quiet Chinese lab, scientists may have just solved one of space technology's biggest puzzles: how to unleash megawatts of energy with microsecond precision. This new satellite power system could change everything we know about orbital technology, from faster space communication to ultra-efficient propulsion. But how exactly did they achieve it? And why is this breakthrough sending shockwaves through the entire aerospace world? Let's uncover the truth. What makes this development truly stand out is the union of high energy and ultra-tight timing in one system, an achievement that's eluded engineers for decades. According to reports from Chinese scientists led by Su Zhenhua at DFH Satellite Co, their prototype delivered 2.6 megawatts of pulsed power and achieved a synchronization accuracy of just 0.63 microseconds during ground testing. Historically, satellite power systems have faced a frustrating trade-off. You either get high power but sloppy timing, or very fine timing but low power. Most older systems produced below 1 megawatt of pulsed power and had synchronization errors measured in milliseconds, not microseconds. The prototype changes that story by combining both megawatt-scale output and near sub-microsecond synchrony. In practical terms, the architecture reportedly draws on solar panels, or equivalent space power generation, then uses high-efficiency DC-DC converters, large energy storage, likely capacitors or pulse-forming networks, and an advanced controller, e.g., an FPGA, tasked with firing 36 modules in tight coordination. That coordination produces the 0.63s synchrony across modules necessary to keep the energy burst coherent. This is significant because many advanced space systems, such as high-energy particle accelerators, high-power lasers, or rapid-fire radar systems, are limited not just by how much power they generate, but how precisely and rapidly they can deliver it. A delayed pulse, mistimed modules, or mismatched phases can cause huge losses or degraded performance. The prototype demonstrates that the power generation and pulse precision barriers can be addressed together. With the prototype's achievement in hand, the next question is, what new possibilities does this unlock in space systems? At its core, the system allows for high-power bursts delivered with fine timing, something that opens doors across several fronts. One application is directed energy systems in orbit. Consider a high-power beam of accelerated particles or a laser that can engage a target quickly at very long distances using stored energy. The article suggests that such a system could disable or neutralize other satellites or missiles in transit by delivering a destructive or disabling pulse of energy. However, even beyond kinetic or offensive uses, the same technology could power ultra-fast laser communications between satellites, high-efficiency ion thrusters for rapid satellite repositioning, or microwave remote sensing with unprecedented sensitivity and power. The researchers themselves propose dual-use scenarios. If this kind of power system becomes orbit-capable, satellites could shift from being passive observers to active players. Satellites could maneuver more aggressively, change orbit faster using high-thrust ion engines, or defend themselves by rapidly redirecting energy. On the communications side, instead of waiting for long transmission windows, high-power laser links could carry vast amounts of data almost instantaneously between orbiters and ground stations. Another aspect: when power delivery becomes flexible and rapid, satellite constellations can be designed to do more than one mission. For example, one satellite might serve as a sensor one moment, then as a communications node the next, then shift to propulsion mode, all by reconfiguring its stored energy burst and control. That kind of versatile architecture changes how we design and deploy space systems. While the prototype is impressive, there are several practical hurdles and strategic dimensions to consider before this becomes a widespread capability. First and foremost, orbit versus lab. The reported 2.6 megawatts pulse and 0.63s synchrony were achieved on the ground, but space brings vacuum, radiation, extreme temperature swings, microgravity effects, and in-orbit heat dissipation challenges. Reports note that surviving and operating under these conditions remains a major engineering gap. Furthermore, Delivering 2.6 megawatts of pulsed power implies large solar arrays or very high-capacity storage systems. In orbit, solar generation is limited by array size, orientation, degradation over time, and eclipse periods. Storage systems must deal with charge/discharge cycles, radiation effects, and thermal management, all while keeping mass and volume within launch constraints. The prototype doesn't yet show those parameters for space deployment. Another factor, targeting and survivability. If we're speaking of a system intended to affect other satellites, then pointing accuracy, beam coherence, and satellite hardening all matter. Many existing satellites are built to cope with radiation, redundancy, and shielding. A high-power burst must still overcome real physical defenses. Experts in the field remain cautious, pointing out that power and precision alone don't guarantee successful outcomes in orbit. From a strategic standpoint, this technology holds dual-use potential. Although civilian applications like high-speed communications or advanced propulsion are promising, the same architecture could underpin systems that change how space assets can function and be protected. That duality means the technology will sit at the confluence of civilian infrastructure, national security policy, and space regulation. For viewers used to astronomical missions, this isn't just about bigger telescopes or wider fields of view. This could reframe how satellites engage with each other and with Earth. The shift is from watching the sky to using space power flows. The step from prototype to deployed system will hinge on 6 factors: generation, storage, thermal/structural design, pointing/stabilization, system integration, and regulatory/operational strategy. The outcome isn't guaranteed, but the trajectory is clear. In summary, what we're observing is a turning point. The technical barrier may be falling, and the strategic implications are broad. Whether this becomes a transformative system or remains a niche remains open, but what's no longer in doubt is that space power is evolving. Thanks for sticking with this exploration of a potential game-changer in space. We've seen how Chinese scientists claim to have broken a decades-old hurdle by delivering both megawatt-scale pulses and microsecond precision. How this opens up new possibilities from lasers and particle beams to high-power propulsion and sensing, and how the real world still holds major questions around orbital implementation, strategy, and arms control. Whether this becomes a tool of science or a tool of power, or both, depends on how the world responds. For now, it's a clear signal. The era of satellites just observing may be rapidly evolving into an era of satellites operating. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Also, you can visit our website, spaceinews.com. Thank you for watching, and see you next time.